Chapter 8 with gases. Last time we got into some gas stoichiometry. Remember, pretty much all stoichiometry is pretty much the same, but really with the gas stoichiometry, still the same steps: balance the equation, convert to moles, do our really stoichiometry part, mole to mole relationship, and our moles to some other unit. And I would say again with gas stoichiometry, probably two places where you will probably just use the ideal gas law. Up front, you would perhaps use the ideal gas law and again solve for N, which would be PV over RT. At that point, you would continue on with a normal sort of stoichiometry problem using the moles. Most commonly, a lot of times you're looking for volume maybe of a gas that you collected. So solving for volume there at the end of the sort of stoichiometry play is also a very common place. Sometimes you may even use both of them, so you may even have to use them both together. It's the second step and the third step. Also, as we talked about, we still want to make sure we watch out for any type of limiting reagent situation that could also develop in the gas stoichiometry problem. We talked about partial pressures, and partial pressures is basically the idea of when you have a mixture of gases, each gas will contribute to the overall total pressure of the mixture. So our total pressure would be the pressure of A plus the pressure of B plus the partial pressure of C. They're referred to as partial pressures because, again, they all sort of contribute to the overall pressure of the mixture of gases. One of the nice things about the ideal sort of aspect of it, of gases, is that even though we may have different gases flying around in the same container, there's going to be, in an ideal situation, really no interaction between any of these gas molecules. And that makes the calculation for the pressures relatively straightforward. We could almost assume that they're in there by themselves, and the presence of, say, gas B and gas C will have really no effect on the pressure of gas A in an ideal situation. So what that reduces down to is pretty much we just can, most cases, can use the ideal gas law and solve for each of the gases individually and then add them together. For that situation, the temperature and the volume will be the same for all the gases that are present in that particular mixture. So really, when you come down to it, even though you may have to do multiple sort of ideal gas law calculations, probably the only real thing that will separate each of the calculations will be the moles of the gases for each of those guys. It's really the kind of the only thing you guys need to calculate. Now, we also saw a situation where maybe you don't have enough information to use the ideal gas law, but you do have a pressure and a way to get to moles of each of the gases that are present in a particular mixture. And you could use this sort of gas situation here, where the partial pressure of the gas you're interested in equals the mole fraction of that gas, which again is the moles of that gas divided by the total moles in the mixture times the total pressure. So this is a nice little equation. It sort of allows you, if you have really that two pieces of information, enough way to get the moles of everybody, and one pressure, either a partial pressure, a total pressure, you'll be able to sort of calculate everything that you need. And probably the last type of partial pressure that we talked about, which is a very common partial pressure situation that occurs, especially in the laboratory, when, for example, you're collecting a gas and water sort of involved. So in that situation, because the gas is sort of displacing the water and the reaction is sort of occurring within water, you will also get the gas that you're interested in this sort of empty space in your collection container, but you'll also get the water vapor with it, and that's the vapor pressure of water. So in that situation, the total pressure will equal the pressure of the gas you're interested in plus the vapor pressure of water. This is a value that you can look up on a table based on temperature. So the nice thing about this one is it's just really a subtraction. It is oftentimes just used really as a sort of correction value to get the pressure of the gas by itself, sometimes referred to as just getting the pressure of the dry gas. Any questions on any of that stuff there that we talked about? So we talked a little bit about kinetic molecular theory of gases, and again, just to go over some of the relationships that we did see with our gas laws. Boyle's law, we saw that the pressure is proportional to the collision rate with the walls. The number density is proportional to 1 over the volume, and the pressure is equal to 1 over the volume. So that was as one goes up, one goes down, the relationship there. Again, smaller volume, going to have a lot more collisions, a lot higher pressure, and vice versa. As we have a larger volume, we'll have less collisions and less pressure. Charles' law, we saw that the average kinetic energy is proportional to the temperature, and pressure is proportional to temperature. So, as we saw with Guy Lusik's law as well, if we have a constant volume situation, obviously, as the pressure increases, we would see the temperature increase as well. Again, the gas molecule is going to be moving faster, and that's going to result in more collisions because the volume is not going to adjust. And again, as the temperature drops, we will see a drop in the pressure. Once again, the volume being in a rigid container, sort of fixed, will not come down to sort of adjust. So we will see a less number of collisions because gas molecules are moving slower. Avogadro's law, we saw the relationship of moles and volume. So remember that allows us in a constant sort of pressure and temperature situation. The number of moles is really proportional to the number of or the volume, I guess is the better way of putting it. And remember, in that situation, if you do have a sort of a gas, one of the aspects of sort of Avogadro's law was the idea that instead of doing a mole to mole relationship, you could do a volume to volume relationship under those conditions. And you could actually do stoichiometry without necessarily having to use the ideal gas law, for example, in a particular equation. And obviously, as we just talked about there, our law of partial pressures, again, just the sum of each individual pressure will give us our total pressure. So let's talk a little bit about gases and speeds. So when we look at a couple of these equations here, or these graphs, we see a couple of situations. On the top left graph is nitrogen gas at different temperatures. So what we see here is at 100 Kelvin. Now, for the vast majority of it, it's kind of running at about that speed. We see at 300, a good majority of the molecules are running at that speed. And at about 700, a good majority of the molecules are really moving at that particular speed. And what we see here is with nitrogen, and what we see with most gases, is if you increase the temperature, which is what we see here, we do see that they are traveling at a much higher velocity and moving a lot faster. And that's what we see when we talk about number of collisions, right? When we increase the temperature, they gain more energy, they start flying around faster, and we get a lot more collisions. Now, if we keep the temperature constant, but look at three different gases here, so we got chlorine, we got nitrogen, and we got helium there. For chlorine here, on average, most of them are heading about that fast. For nitrogen, they're heading about that fast, and for helium, they're heading about that fast. And what we see here is at the same temperature, there is a difference in the gas molecules. And really, as we kind of alluded to in that partial pressure question we did, it is based off of molar mass. And what we see here is helium is the lightest of all the gas molecules there, and it is traveling faster. And out of these three here, chlorine is the heaviest of the three gas molecules. So because it has a greater molar mass, it's going to be traveling slower because it's heavier at the same temperature. So if you remember, again, we saw, I think, helium contributed a lot more to the partial pressure in that mixture than we saw with neon. You could actually calculate how fast a gas molecule is going by calculating the RMS. This is what is known as the root mean square velocity, the RMS. And it is in typically units of meters per second is basically what you would calculate. And this is the square root of 3 times R times the temperature, and this is the molar mass. So let's talk a little bit about the units here. First off, the R here is actually the bless you, the gas constant that has energy, 8.314 joules per Kelvin per mole is the R that we want to use here. It is not the 0.08206 that we use in a gas law sort of situation here. The reason for that is a couple of things. Our temperature does need to be in Kelvin. And our molar mass, because we are using that R, actually needs to be in kilograms per mole rather than grams per mole. The reason it needs to be in kilograms per mole rather than grams per mole is because a joule, which I think we saw in a much earlier chapter this semester, is equal to a kilogram meter squared second squared. So that is also where the meters per second comes out. When you do solve for this, it comes from that sort of unit. So if we just look at this in terms of units, we will have basically the square root of up on top for our R. We will have kilograms, meters squared, seconds squared. We will also still have Kelvin and mole. So that is kind of the units for R there. Obviously, our temperature unit would be Kelvin divided by our molar mass in kilograms per mole. So when we put all these units into that square root, what happens is our Kelvin will cancel, our moles will cancel, our kilograms will cancel. And what we are left with when we're all said and done canceling out all those units is meters squared over second squared. And then when we take the square root of it, we end up with meters per second. So that is how we get to basically meters per second. It is from the unit of joules, that is a kilogram meter squared second squared. And again, you want to make sure you're using the 8.314 version of it. And again, as I mentioned, you want to make sure that you are using the molar mass in kilograms per mole, not grams per mole. Otherwise, you'll be off by a factor of 1,000. Any questions on that there? So why don't we try that? Actually, let's do both of those guys. Let's do the two that we saw there. Calculate the RMS, the root mean square velocity in meters per second for helium and neon at 27 degrees Celsius. So once again, helium 4.003, 2018 for neon. All right, so take a few moments there, calculate it up, see what you come up with. Look, so once again, we're going to calculate the root mean square velocity, which is the square root of 3RT divided by the molar mass. We do obviously, like normal, got to convert our temperature into Kelvin here. So that's going to be 300 Kelvin. Remember, again, for this particular one, the R is actually the energy one, which is the 8.314 joules per Kelvin per mole. And again, basically it's the same number, which is good. Basically, though, if you get rid of the joules, you'll end up with units that look something like this. Again, with obviously this part of it here being the joule part of it. That's where that comes from. So at this point here, that is also the determining factor because there is a kilogram here. We do need to convert our molar mass from grams per mole into kilograms per mole. So if we did it for helium, that is 4.003 grams per mole. Again, there are 1,000 grams in a kilogram, so we'll convert that, basically move the decimal place over a few places, should take care of it. And that will give us something like 0.004003 kilograms per mole. We'll do the same thing here for our neon. We'll take 2018 grams per mole, also convert it into kilograms per mole. And again, we need to do this so that everything cancels out correctly in terms of units, again, with really our joule part of it. Now that we have everything, we could calculate it for each of them. So we'll start with helium. Helium's root mean square velocity would equal the square root of 3 times 8.314. Once again, kilograms, meters squared, seconds squared, Kelvin mole. Times our temperature in Kelvin, divided by, again, our molar mass here in kilograms per mole. Again, the kelvins will cancel, the moles will cancel, the kilograms will cancel, giving us meters squared over seconds squared, which is going to become meters per second once we take the square root of it. So 3 times 8.314 times 300 divided by 0.004003, and also take the square root of it would be good. So we're shooting at something here for helium of like 1,367 meters per second. It's its velocity of how fast it is traveling at this particular temperature. Any question on that calculation there? Now, if we do pretty much the same calculation here for our other gas that's in that mixture, which is neon, root mean square velocity will be fairly similar, calculated 3 times our 8.314 kilograms meters squared, second squared, Kelvin mole, our 300 Kelvin divided by, again, its molar mass in kilograms per mole. So 2018 kilograms per mole. Once again, moles cancel, Kelvin cancel, kilograms cancel. And that's going to get us something like about, we'll call it 608.9 meters per second. So we could see roughly here, we have our helium is traveling about twice as fast as our neon was. And again, if you think back to that partial pressure problem where we did it, that's why, again, our helium is contributing like 12 point, whatever it was, 12.3 atmospheres of the 14 total atmospheres. It is traveling much faster, which means it's going to have a lot more collisions. So helium is traveling about 3,000 miles per hour, while neon is traveling about 1,300 miles per hour. So, they're moving a lot faster, helium, because it is a much lighter gas. Any questions on that? Yeah. Yeah, I would, for example, the top one here, I would take 3 times 8.314 times 300, it equals. And then I would divide it by the bottom number there, the 0.004003, it equals, and then take the square root of that answer. Yeah, so I would do it that way rather than trying to, I don't know, put it all in with like parentheses and all that. So I would start that way, work what's inside, just like normal, everything on top, hit equals, divide what's on bottom, hit equals, and then just take the square root of the answer. Other questions? All right, so this is root mean squared velocity, which allows you, again, to calculate how fast a gas molecule is moving, and it reinforces what we saw in that partial pressure problem. Again, because helium is lighter, it is definitely traveling a lot faster than neon, which is heavier, and thus, because of that, it is causing a lot more collisions and a lot more pressure, like we saw in that partial pressure problem yesterday. Any questions on any part of that? So again, the key on this one is to remember to use the correct R value. And also, obviously, that the molar mass has to be in that kilograms for everything to properly cancel out. So let's talk a little about some other properties here of gases, and one is gas diffusion. And we have two bottles here, for example, NH3 and HCl. And when they do come together, they will make ammonium chloride. And gas diffusion is the gradual mixing of molecules of one gas by another based on their kinetic properties. And we see that they are mixing. So if you open this up, the vapors of each of them are going to come out and start to mix. What we do see in terms of where they're mixing is they're actually mixing much closer to the HCl bottle, right? So if we take a look at it, we can see that these gases are basically coming together much closer to that HCl bottle. And the reason for this is also what we have been talking about here and just talked about. If we look at the molar masses of each of these gases, we do see that ammonia is lighter. So as we've just been talking about, we should expect it to have a much higher root mean square velocity. It should be moving a lot faster. And because this will be moving a lot faster than the slower moving HCl, which is heavier, is able to get closer to the HCl bottle, and the mixing starts to occur near the slower moving gas molecules. So again, this sort of reinforces what we've been talking about, that lighter gas is moving a lot faster. You could actually calculate a couple of things if you know how fast a gas is moving and the molar mass. This is the rate of gas one. So that's the rate of gas one. This is the molar mass of gas one. And that is the molar mass, obviously, of gas two, and that is the rate of gas two. So you can use this, for example, if you do have some information about how maybe one gas is moving versus the other, you can figure out the rate of how fast the other gas would be moving. You could also, if you know the rate of two gases and maybe the molar mass of one, you can figure out the molar mass of another. So gas diffusion is a gradual mix of molecules based on basically their kinetic properties, how fast they're moving. There's also gas effusion. Gas effusion is the excuse me, is the process in which gas under pressure basically escapes through, say, a hole. So like this little hole right here, these gas molecules pop out to the other side and escapes from one compartment to the next. And it's a very similar sort of calculation. You take the rate of each of those and how they're moving, or you could take the time it takes for each of those guys to get there. And again, these are the molar masses of our two gas molecules. So for example here, nickel forms a gaseous compound of a form of NiCO, and I'm not sure what it is. What is the value of X under these conditions if methane effuses 3.3 times faster than that compound? So why don't you give it a try and see what you come up with here. And I'm going to give you some information here. Nickel is an unknown, what the molar mass of that unknown is. And from the molar mass, we should be able to figure out sort of what is the missing part of the formula. So in this case, it really doesn't matter sort of which one you label which. You just got to keep, in this case, perhaps we're going to do sort of R1 over R2 is equal to the square root of M2, M1. You just got to keep, obviously, the one informations together and the two informations together. So if I go with R1 as the rate of my unknown guy, my nickel, coal, carbon, oxygen guy. And we know that M1 is obviously what we're looking for in this case. What we know is that methane effuses 3.3 times faster than the carbon or the compound. That means that R2 would be our methane. And we know that it is 3.3 times faster than R1, basically. That's what it says. And we can figure out the molar mass of methane, which is our M2, by obviously using the periodic table. So in this particular case here, we got 12.01 plus 4 times 1.008 for the hydrogen. So for methane, we're looking at a molar mass here of about 1604. Would be what we need here, 1604 grams per mole. All right, so now that we have that, we could actually put it into our sort of equation here. So we have R1, which is our unknown compound, divided by R2, which is 3.3 R1, equals the square root of M2, which is 1604 grams per mole, divided by M1. Any questions on that there? At this point, although we don't know what R1 is, we do know that it should cancel out. So that's going to cancel out. And that will get me here. That will get me basically 1 over 3.3, which is equal to the square root of 16.04 divided by M1. To get rid of the square root, I need to square both sides, right? So I got to square both sides, basically. So we're going to square both sides. So if we square both sides, 1 divided by 3.3 and then square it, you'll find that on my calculator, will give us something like 0.091827 is equal to, that basically just gets rid of the square root on the other side. So mathematically, I need to multiply M1 to each side and then divide by this back to the other side. 27, I think. Those guys are going to cancel. And that is going to give me a molar mass of 16.04 divided by my 0.0918 number there. And that's going to give us, I'll just go up here so it might be easier to see, an M1 of 174.7 grams per mole. Any questions so far on the calculation part? Now, how's that number going to help us when we're really trying to find out what is the actual formula for this? So that number could help us because we know if we look at the formula, I just maybe erase some things here, get rid of this here. If we look at the molar mass here that we just calculated, that is obviously based off of this formula here, which is NiCOX. What we know is if we take our 174.7 grams per mole, we know from the formula that we have only one nickel, right? So we definitely could subtract off the nickel's mass, 5869. And again, that's for our nickel, basically. So if we do that, 174.7 minus 58.69, that's going to give us 116.01 grams per mole. That 116 grams per mole is going to come from how many units basically of carbon and oxygen together. That's basically what the little subscript means. There's so many units of carbon and oxygen together. So we know that if we add up carbon and oxygen here, we got 16 plus 12.01. Each carbon oxygen unit, if we add that together, is 28.01. So if I take this 116 and divide it by 2801, that will basically tell me how many carbon oxygen units I have. So if I do that and divide it by 2801, I get roughly 4.1, which is close enough to 4. And that means that I should have 4 of those carbon oxygen units present in this case. Any questions on that? So here you can see we could use the effusion information to figure out the molar mass of an unknown, and using the molar mass, we could basically figure out what its proper formula should be. Any questions on that there? Now, in this case, I chose R1 and M1 as kind of the unknown. Again, you could have chose the R2 and M2 as that, and it would basically come out the same. Any questions on gas effusion here? All right. So what we're going to finish up talking about here in terms of gases is the idea of sort of real gases. So up until this point, we've talked about ideal gases basically, and most of the time when you're dealing with gases, you assume sort of ideal conditions. but there is some deviations that can occur from ideal situation under really large pressures and low temperatures. So when you have those things, you do deviate from ideal behavior. And we get gases, which are sometimes referred to as real gases, are non-ideal gases, is what happens in this situation. So if we take the ideal gas law and we solve for n, we will get a ratio of PV over RT that is equal to 1 in an ideal situation. You could see that when we look at this graph, as we get to really high pressures, we start to get some deviation, obviously, from ideal behavior. These lines definitely are deviating from the ideal situation. And under these conditions, we do have to take into account those two things that we sort of ignore in the ideal gas situation, which is the volume of the gas is basically zero or negligible, and the interactions between gas molecules. The attractive forces and the repulsive forces. So under these sort of non-ideal situations and these real gas situations, those attractive forces and repulsive forces come into play. So if you just think about sort of Boyle's law, what we talked about in the relationship between pressure and volume, when we hit these really high pressures, that means, frankly, we have probably in terms of volume, a very, very small volume, which means our gas molecules, there's a couple more important things for it. As you can see with my picture there in a very small volume at these really high pressures, the volume of the gas itself is actually relevant versus the volume of the container it's in, because it's almost as big as the size of the container in this case. So you do have to take into account the volume of the actual gas molecule as well. You could also see that all the gas molecules are super close to one another, and that means that they will be hanging around each other for a much longer period of time. And that also means that you have to take into account how they interact with one another when you have these sort of real gas situations, non-ideal situations. Again, dramatically drawn here, if you have, a sort of ideal situation, you have a gas molecule whose volume and relative to the volume of the container is super small compared to the container size. So, you don't have to really take it into account. So you can think of it like if you had a big, like, I don't know, big like trash can or something like that, or a trash can, if you threw like a golf ball in there, the volume of the golf ball versus the volume of the trash can is going to be relatively small. But if you threw like a giant basketball in there, it might even get stuck, right? So the volume of the basketball is really relevant versus the volume of the container that it's in. Now, we'll talk about really in a second why a lot of times we do deal with ideal gases, but under these situations, these are what are referred to as real gases. So real gases do not behave like ideal gases, and these are really the conditions where we sort of get into our real gas situation. As I mentioned a second ago, as we saw in that graph, under high pressures, that's again going to result in a much smaller volume and also really low temperatures. So what does the temperature has to do with it? Temperature has to do with it is at really low temperatures, there's probably not going to be moving as fast. So your gas molecules are going to be moving much, much slower, which means instead of the gas molecules just whizzing by each other, right? They're going to be moving a lot slower, which means they will be in contact with each other for a much longer period of time. And again, that is where we have to take into account how they interact with one another, because they're actually going to be near each other for a much longer period of time. So that is the two things for kinetic molecular theory that we talked about. Gas molecules volume do not take up space, and there's no attractive forces. At low temperatures and high pressures, these assumptions aren't valid for those reasons I just talked about. Again, they're going to be near each other for a much longer period of time, and they're going to be probably in a much smaller volume, and thus the volume of the gas molecules are really important. So when we look at molecules that take up space, the molar volume of a real gas is larger than predicted by the ideal gas law at higher pressures. So under ideal situations, this is the red line. That is what we would expect the molar volume of a gas. That is our 22.414 liters. molar volume of a gas. And what we see here is it starts to vary and become larger as this green line is higher up. So it has a larger molar volume than it does under ideal conditions. And again, at these high pressures, we have an overall smaller volume, making the volume of the gas much more important. The effect on that is at higher pressures, the amount of space occupied by the molecules is going to be significant to the total volume. And the molecular volume will actually be larger than predicted by the ideal gas law. So a guy by the name of van der Waals came up with really some correction values and factors that can be used to correct for real gases. And it basically kind of builds off of the ideal gas law, but it gives you these sort of correction factors. And the correction factor for the volume is the B constant, or the B van der Waals constant, and that is different for every gas. So there are two van der Waals constants for real gases, A and B, and you can look them up on a table for different gases. They will be different values. And that is sort of the correction value to the ideal gas law that is used to correct for sort of the increase in volume that we would expect in a non-ideal situation or a real gas situation. Now, the other sort of effect is, as we talked about, under real gas conditions, there is going to be attractive forces and repulsion forces between gas molecules. And we see that the molar volume is actually smaller at lower temperatures than predicted. So molar volume gets smaller at lower temperatures. Now, why is the attractive forces important? Well, if you think about sort of in an ideal situation, for example, if you have a gas molecule, it's free to just fly around and hit the container and the walls of the container. There's nothing that's going to prevent it from sort of slowing down, perhaps, or speeding up. But if you have sort of a real gas situation where maybe you got some attraction now between this gas molecule and other gas molecules in there, it's going to probably slow it up, for example, if it's attraction forces, and it's going to take longer or may not hit the wall with the same sort of force as it would if there was no attraction happening. Thus, we would end up with a smaller sort of pressure that would occur. So this will affect sort of the pressure on it. And there is a correction value that van der Waals did for correction for pressure, and that is what is known as the A value there. And again, that is a correction value that you could look up on a table for van der Waals constants. Now, putting these together, this is sort of what happens with the ideal gas law is it gets sort of modified with these correction values for the specific gases you're dealing with. And that's what I was mentioning before. Obviously, here, this gas molecule, if it does experience attractive forces, is not going to hit the wall as hard, or even it might even hit it harder if it is some repulsion type forces that it actually feels. So it'll kind of bounce away a lot faster as well. So under ideal conditions, we don't take that into account, but here in real gas conditions, we do. And that gives us our van der Waals equation for real gases or non-ideal gases. It is a scary looking ideal gas law, pretty much. So a reminder, right, our ideal gas law is PV equals nRT. And again, this is a table, and you have one in your book similar to this, an A and a B table. These are van der Waals constants. They are, as you can see, different values for different gases, which means one of the sort of aspects of sort of the van der Waals equation in real gases is this equation is not necessarily very universal. It is kind of specific for that specific gas you're doing because you got to grab the A and B constants for that specific gas that you're using. The ideal gas law, which we use in most cases, and that's why we assume in a lot of cases, sort of ideal conditions, is more of a universal sort of formula because there is no dependence on if this gas I need to use these constants, or if it's this gas I have to use these constants. There is no sort of correction values. So it's more universally sort of used. All this is the same as the ideal gas law. So this is still your pressure in atmosphere. This is still your moles. This is still your volume in liters. That is still moles. That is still your gas constant. That's your temperature in Kelvin and obviously your moles. So you do want to always make sure if you happen to look up these values in a table, you do want to make sure that they are in the correct units. Sometimes they may not be given to you in atmospheres. They may be given to you as some other unit of pressure that you might have to do some conversions. So if you do grab some of these values off of a table, you should make sure you always look at the A and B sort of units and make sure that they will agree with obviously the gas that we put in there into the van der Waals equation. So van der Waals equation, again, used for non-ideal situations, real gases. It takes into account a correction value for the pressure based on the attractive forces. And it also takes on a correction value for the volume based on the idea that under these sort of high pressure, low temperature situations, we do have to take into effect, basically, or take into account the volume of the gas itself. Any questions on that there? You plug and chug into that equation just like the ideal gas law, basically, and solve for what you need. So why do we, under a lot of cases, think about using really just sort of the ideal gas law in most cases? Because in most cases, if you think about it, you can kind of see it here, probably in this graph better. Oops. So if you think about sort of the pressure situation, right? Most standard pressure is 1 atmosphere, which would be like right in this ballpark. So even a little bit higher than 1 atmosphere, or even that, it's way less than like 100 atmospheres or 200 atmospheres. Even in those sort of conditions, if it's a little bit above 1 atmosphere and stuff like that, those lines are not deviating all that much from the ideal situation. So even in those sort of slightly higher than 1 atmosphere and the normal sort of conditions, we can still apply the ideal gas law in an ideal situation and use the ideal gas law. But definitely if we start cranking, in the 100-ish atmospheres or so, you were getting a lot of deviation to starting to occur. And this is where you would have to come into account with the real gas sort of law, the van der Waals equation, to account for that. But again, a majority of the time, pressure wise, we're hanging out right back here where this starts. And again, there's not that great of a deviation from ideal situations, which is why in a lot of cases we do just kind of go with the ideal gas situation. But if it is really high or stuff or something to do with van der Waals constants, that is the kind of scarier looking equation there at the end there that would need to be used. Any questions on that there? Okay. That we just talked about in gases, exam 3 coming up on Monday. Yeah. So in this chapter, we're going to talk about the liquid state. We're going to talk about a few other things as well, how molecules interact with one another. So let's get into that. So the first thing we're going to talk about, are really the majority of what we're going to talk about here, is intermolecular forces. And I think we touched upon intermolecular forces in a little earlier chapter, but intermolecular forces is really the attractive forces that holds one molecule together with another. So it is how one entire molecule is held together to another. It could be the same two molecules basically held together. It could be different molecules held together, but it is basically how this molecule, for example, and this molecule interact with one another. Pretty much all intermolecular forces is a basic attraction force that occurs. It is basically the positive side of one molecule is attracted to the negative side of another. So it is the opposites attraction happening there. The electrostatic attraction is what it holds basically an intermolecular force together. It is responsible for things like boiling points, melting points, freezing points. These are responsible for those things. So for example, if you take something like water, negative, more negative on the oxygen, more positive there on the hydrogen. This would be a intermolecular force when like the negative side of one water is attracted to the positive side of another, for example. It is also really important for things like solubility. how things interact with each other, how different molecules, for example, interact, why certain things are soluble in each other and why certain things are not soluble in each other. So, they're responsible for like things like solubility and the how things sort of interact with each other. Now, an intramolecular force, as we might have talked about a little bit, an intramolecular force means within the molecule, and that is the force that holds basically atoms together in a molecule and is responsible for the stability of it. So these are things like ionic bonding, covalent bonding, where they're sharing electrons and stuff like that. So if you took, again, just one individual water molecule, it is the sharing of electrons here between this oxygen and hydrogen and that oxygen and hydrogen, basically the bonds within the molecule of what holds that together. Also, something like an ionic compound, it's the electrostatic attraction between the positive cation and the negative anion that holds an ionic solid together, which is a super strong attractive force. Now, again, I think we might have talked about it at the beginning of the gas chapter, but usually the intermolecular forces are usually much weaker than the intramolecular forces. And again, the sort of overwhelmingly common example of that is water. And again, the negative side of one, positive side of another, going to bond with through what is known as hydrogen bonding, and that's our intermolecular force. And we know that when we heat something like water in the liquid phase, it is actually the bond between the two water molecules that break first, freeing this guy and this water molecule to go into the gas phase, right? And kind of free them up. And we know that for a fact because, again, if it was opposite the situation and you started heating it up and the intramolecular forces were much weaker than the intermolecular forces, we would start breaking these bonds first. And that would produce hydrogen gas and oxygen gas, which once again, probably wouldn't be a great thing if you're boiling water to make pasta, because you might not get to the pasta part in that case, right? Because we don't produce hydrogen gas or oxygen gas when we just like boil water, right? So the strength of that intramolecular force much, much stronger, holds the entire molecule together, but the force between two different molecules is much, much weaker, which is that intermolecular force. So this does not happen. So what we're going to talk about and focus in on here in the first part of this chapter is really intermolecular forces. So once again, these are our forces that hold one entire molecule together with another. And again, it could be two of the same molecules, it could be different molecules, but this is how they happen. The first type of intermolecular force is what is known as a dipole-dipole force. And you might remember dipole, we see dipole and a dipole moment in our polar molecules, right? They have a overall dipole moment where one side of the molecule is more negative, the other side is more positive due to the overall unequal sharing of electrons that is occurring. So in a dipole-dipole force, the molecules basically arrange each other in a way to maximize the positive and negative attraction. So what does that mean? It means that this is the main force for a polar molecule to interact with another polar molecule, which again could be the two same molecules or two different polar molecules, and they do not have the ability to hydrogen bond. So basically, you will have one polar molecule that has a positive and negative side, and you'll have another polar molecule that has a positive negative side, and those opposite sides is where that attraction is going to happen, and that is how they're going to kind of hold each other together, is through that opposite attraction. Because they are a polar molecule, and because they have a dipole moment, it means that no matter what you do to that polar molecule, it will always have a positive side and a negative side. No matter what happens, it's kind of good to go in the sense of being able to interact this way. It's always got a positive side, it's always got a negative side. It's ready to go. It can interact with somebody else that has a positive negative side. It doesn't need anything to happen for it to get a positive or negative side. It's kind of built in, ready to go to interact this way. Now, obviously, especially when you come together, say in a solid state or something like that, there's going to be negative sides near negatives and positive sides of molecules near positive sides of molecules. And they really do not want to be near each other because they don't want the same attraction or same sign of attraction near each other. So they will sort of wiggle around a little bit and kind of move around to find a spot where they could kind of maximize the attractive forces between the positive and negative side and minimize those repulsion forces between the, say, two negative sides and two positive sides. And that's what we see here. Again, they will really start shifting and moving around until they kind of lock into a place where they will be maximizing these attractive forces but minimizing sort of the repulsion forces of like two positives near each other or two negatives near each other. But it's going to happen no matter how you do it because there is a positive and negative side of those molecules, but they will continue to move until they find a nice energy alignment that they can maximize those attractive forces. Now, another type of interaction is one that is referred to as an ion dipole force. And an ion dipole force is pretty much what it sounds like. It is an ion and a polar molecule. So this is basically what happens when we dissolve an ionic compound in something like water. Right. We know that when we dissolve something like sodium chloride, there's a positive ion and a negative ion. And we know something like water is polar. And it is the negative side of water that will end up surrounding the positive ion, for example, which is the oxygen is the negative side of water, and is the positive side of water, which is the hydrogens that will end up surrounding the negative ion. And as we talked about, this is essentially how stuff dissolves, or an ionic compound dissolves. It also doesn't disappear, it just gets meshed in there with a bunch of water molecules that we no longer can see it. But it is that sort of simple attraction between opposite charges that allows this to occur. The strength of the depends on the charge of the ion or the dipole. For equal charges of cations, they are attracted strongly to the anions, and the cations are usually smaller than the anions as well. So because of that, they kind of get sucked in a lot stronger. Ionic compounds have low solubility in nonpolar solvents, and that is why water's a really good solvent for something that's ionic because it's polar. A nonpolar solvent would have no charge, which means essentially it has no charge. So it makes it really hard to interact with something that does have a charge. They don't have that way to sort of interact sort of oppositely, positive and negative or negative and positive. So that's why when we put something like an ionic compound into a nonpolar solvent like Br2 or something like that, it pretty much will not dissolve because of that sort of interaction where it can't really interact well with one another. Now, dispersion forces are the forces that essentially will be used by nonpolar molecules. So this is the main intermolecular force for nonpolar molecules. And as I just mentioned a second ago, if you have a nonpolar molecule, that basically means that we have an equal separation of charge and electrons over the whole molecule. It basically, for all intents purposes, means it's neutral. There's like really no charge happening here, right? In a nonpolar molecule. So the problem with that is it needs a charge to sort of be able to interact with things. And there's really a couple ways that you can sort of force, if you will, are for a nonpolar molecule to sort of gain a charge. And these are going to be able to gain a charge and become temporarily like a separation of charge. So they'll be able to temporarily sort of gain a charge. One way that you could do that is what is known as an induced dipole interaction, an ion-induced dipole interaction. That means that if you rolled up on a nonpolar molecule with something like a cation that has a positive charge, what's going to happen is temporarily the electrons in this neutral guy are going to be attracted to that positive charge from the ion. And that's going to, as I just said a second ago, temporarily cause this nonpolar guy to sort of gain a charge and have a separation charge where there's a more positive side and a more negative side to this nonpolar molecule. That's going to allow it to, again, temporarily have a way to interact with that ion. And the same thing could happen with a polar molecule. If you dump a polar molecule in with a nonpolar molecule, you will create temporarily a dipole-induced dipole, which is what we see down here. This is a polar molecule, which has that separation of charge. And the same thing is going to happen if you roll up on a nonpolar guy with a polar molecule. The electrons will go away from the negative side and cause this guy to temporarily gain a charge. And now they have a way to interact with one another temporarily. And that's what we see here. They will temporarily be able to do that. It is temporary because as soon as that ion kind of floats away, or the polar molecule floats away, that nonpolar guy is going to lose that temporary change of charge and kind of fall back into its normal neutral sort of arrangement. That makes these type of forces relatively weak. That is also why, if you remember, or if you know, if you take something that's polar and nonpolar and mix it up like oil and vinegar salad dressing, right? If you mix it up, it will stay mixed for a while, right? But over a long period of time, it will all separate out, right? You'll see kind of the oil part, the vinegar part, everything will kind of separate out into two different layers. So although they can interact for a short period of time through these dispersion forces, because everybody can kind of use dispersion forces for a little bit, over the long period of time, there's no way to maintain that interaction. So everything sort of separates out and they can't maintain that interaction, which again is why these are very, very weak type of intermolecular forces. Another very common way that nonpolar, for example, molecules interact with other nonpolar molecules is through what is known as polarizability. And polarizability is really the way that a molecule can sort of separate out its electrons. So I guess a better way of wording that is we have a nonpolar molecule, for example, here, and we do have electrons that are just flying around basically, right? So they're moving around randomly about the atom. And it could happen upon that at some point in time, all the electrons decide to vacation kind of to the right-hand side of this molecule, right? And if they do that, what that's going to create is a temporary charge of negative happening on that side. The other side will temporarily become positively charged because the electrons are kind of hanging out on the other side of the molecule. And that will happen. And if it happens to be next to another nonpolar molecule, because of this negative sign here, the electrons in this guy is now going to head off to the other side. And now you had two nonpolar molecules that didn't have a charge, but because of this incident that just occurred here, they both will now gain sort of a positive negative side. And now they have a way to temporarily basically interact with one another. And this is what polarizability is. It's the ability of those electrons to sort of go, one side versus the other, sort of move from one place to the next. And that's the ease at which those electrons can be distributed or distorted. There is a sort of way that could happen a lot easier, and it does involve molar mass. So the greater the molar mass of, say, a compound that would use a dispersion force, there is a greater opportunity for those electrons to kind of move from one place to the next And that's because there's just a lot more electrons. So if you have a greater molar mass, you have more atoms. More atoms means you have more electrons. So there's a greater opportunity for that to occur. There's also a lot more places where interactions can actually occur between molecules. So the strength of this very weak force actually increases with increasing molar mass because of the more electrons being present. So even though it's really weak intermolecular force, you can have a stronger dispersion force, which is a weaker force, based on how much electrons and molar mass that you have. This is what is sometimes referred to as an instantaneous dipole. It will kind of make and break these sort of instantaneous dipoles. And this is what keeps nonpolar molecules basically together. This is also why when you look at something like a nonpolar molecule, which is essentially the main force is the dispersion forces. Usually will have very low boiling points and melting points because they're held together by these really temporary sort of interactions. They need something to happen for them to really be able to interact with one another, and they are not always ready to go. They're basically neutral, so they're not ready to go. And that's the major difference between, say, a nonpolar molecule and a polar molecule. A polar molecule, as I was saying earlier, pretty much is good to go. It will always have a negative side and positive side. So if you take a water molecule, no matter what you do with it, or where you take it from, what you do with it, it always has that positive and negative side. So it's always good to go for these intermolecular forces. If you take something like methane, it doesn't really have a positive or negative side. It needs something to happen for those interactions. That's also why, if you think about a lot of nonpolar molecules, which are a lot of them are organic molecules like methane, propane, butane. Those are three kind of the first four organic molecules. They're all pretty much gases under normal conditions, and that's because they're held together with this really weak sort of intermolecular force. You just sneeze at them wrong and they will go into the gas phase. That's also why if you end up taking organic chemistry, a lot of organic molecules, which are nonpolar, are very volatile, which means they can go into the gas phase really, really easily. And that's because even though they may be in the liquid phase, they're held together by these really weak dispersion forces. And it doesn't take a lot for them to kind of break apart and escape each other and go into the gas phase and end up as a gas, which is why they stick you in a fume hood when you're in organic chemistry. So you don't inhale all those vapors that come off from those volatile organic compounds. Now, dispersion forces, the attraction does rise as a result of these temporary induced dipoles. These are dispersion forces. And again, the larger the molecules, the more electrons, so the stronger the dispersion forces. Dipole, 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 induced dipole, and dispersion forces are sometimes referred to as van der Waals first forces. Hence our van der Waals equation we just saw there at the end of the gas chapter. He did a lot of work with how molecules interact with other molecules as well. Now, this is an example of an instantaneous dipole, as I mentioned, just because those electrons sort of separate sides, it will cause the separation of charge, causing this guy now to have a separation charge. And now there's a partially positive side, partially negative side near each other. And now these two guys can basically interact with one another. Now, another type of intermolecular force, which is a really important force, is hydrogen bonding. And it really is a type of dipole-dipole interaction. In order for you to have hydrogen bonding, you need to have a bond between a hydrogen atom and a polar atom, such as our friends nitrogen, oxygen, or fluorine. So if you look at the periodic table, nitrogen, oxygen, fluorine is up on top. That is the three most electronegative atoms, right? So obviously, if you have a bond between hydrogen and fluorine, you're going to have a pretty polar bond. If you remember, I think we did the electronegativity, and that's like 1.9, which is pretty close to electrons jumping ship. And that creates a really, really polar type of bond that occurs. So you need to have a hydrogen that is directly bonded to either a nitrogen, oxygen, or fluorine for the ability to hydrogen bond. And this is the major bonding that we see in water. Water, again, negative and positive. Negative and positive. And again, the bond between the oxygen and the hydrogen there is a hydrogen bonding happening. It's able to do so because this hydrogen and this hydrogen are directly attached to an oxygen. So again, they're directly attached to an oxygen, which allows it to do that. Again, CH4 hydrogen bond. CH4 cannot hydrogen bond, even though it has a ton of hydrogens. None of those hydrogens are directly attached to a nitrogen, oxygen, or fluorine. And by the way, the carbon-hydrogen bond is nonpolar as well, right? So this guy here cannot hydrogen bond, even though there are hydrogens there. It would actually use dispersion forces, which is a pretty weak type of force to interact with something. How about ammonia? Can it hydrogen bond? Ammonia can hydrogen bond. It's a polar molecule. It also has a nitrogen directly attached to a hydrogen, and it can do hydrogen bonding as well. So again, just because there's a hydrogen present doesn't mean it has the ability to hydrogen bond. It needs to be directly attached to one of those things, a nitrogen, oxygen, or a fluorine to be able to do so. Any questions on that? So here's some hydrogen bonding that we see there. And again, we see some opposite attraction happening here between these two types of molecules. Hydrogen bonding also accounts for why things are sort of, for example, soluble. For example, if we took something like methanol, which is an organic compound, and we took something like water, because methanol kind of has two parts, it has a nonpolar part here, but it does have this bond here, which is also polar, which means that's more negative, that's more positive. So that gives it the ability to interact well with water. So even though this guy's got a little bit of a nonpolar part, the methanol, it does have that one bond, which is OH, which allows it to interact well with water and be very soluble in it because of that. So these intermolecular forces affect things like solubility as well. It does have its limit. For example, if you were to add another 5 carbons to that side, the solubility would go down to almost nothing. And that's because it just gets really, really big and too big to interact well with water. So it kind of gets in the way of the interaction. But things that do have similar types of interactions tend to be soluble in each other because they're able to interact with each other the same way that each guy is able to interact with itself. So if you have things that are able to interact with each other the same way they interact with themselves through these intermolecular forces, that definitely makes things much, much more soluble with each other. That is why when we take something that's polar, that wants to use something that's a dipole-dipole or hydrogen bonding, and something that is nonpolar that wants to use dispersion forces, they have a very difficult time interacting with each other because those are very, very different types of interactions. So it has a really, really problematic approach that they typically are not going to be soluble in each other. So when we talk about our intermolecular forces in terms of strength, the strongest intermolecular force you could have would be hydrogen bonding in a sense. And that again is a bond between hydrogen and a nitrogen, oxygen, or fluorine. That's going to be your strongest. Next would be some type of dipole-dipole. And again, hydrogen bonding is for polar molecules that can hydrogen bond. Dipole-dipole is for polar molecules that typically do not hydrogen bond. So if you had something like something like this is be polar. It would use something that is going to be dipole as its main interaction. And the weakest of all those are dispersion forces. So dispersion forces, those induced dipoles, those instantaneous dipoles, this is the main force for nonpolar molecules. And it is the weakest. Something like methane, for example. This is also why, if you think about sort of that experiment we did way back when, where we put like we use heptane, I think in your case, heptane, which was a nonpolar solvent, and we have those different layers. That is why what we saw was up here in this layer, for example, was the Br2. That is a nonpolar molecule going to be very soluble in this nonpolar because they're both going to be using dispersion forces. If you remember when we put something like sodium chloride in there, it actually was on the bottom, which was the water layer, right? And water being polar, these guys are going to be able to do ion dipole interaction, be surrounded by the waters and so forth. And that's why when we did that sort of experiment, we knew where each of those things should be based on the interaction that should occur between those molecules in, say, heptane, those molecules in water, again, the nonpolar versus polar. So typically, polar and polar things soluble in each other. Ionic and polar things are soluble in each other. Nonpolar and nonpolar things are usually soluble in each other. Again, all these interactions are going to use very similar interactions to one another and make them mix really well. But basically, insoluble are typically when you try to mix a polar and a nonpolar. Again, these are very weak forces because it does rely upon something happening in order for them to interact. These guys, which are the main forces in polar molecules, are good to go like